Physics 2212, Lab 3, Magnetic Field of a Bar Magnet. Introduction. Here's our purpose. Measure the distance dependence of the magnetic field due to a small bar magnet and compare your measurements to the distance dependence predicted by the equations for the on and off axis magnetic fields derived from the Biot-Savart law. The fundamentals we use in this lab. The Biot-Savart law, the distance dependence equation, and the magnetic field on axis right here. Models. We modeled the bar magnet and displayed the magnetic field at various points around the magnet. Results. We found N to be negative 4.34, K to be 1.83 times 10 to the negative 8th, U, micro I guess, to be 0.0915, and then B net is 6.20759. And I'll go over those calculations later on in the video. Experiment. Our system was the magnetometer and the magnet. Surroundings was everything else. Our initial conditions was the magnitude of Bx was 0, and the magnitude of By was about 49 times 10 to the negative 6 Teslas. Next. So first we found the magnetometer chip in my phone. Next, we measured the distance from the magnet to the magnetometer that produced a certain magnitude of Bx to observe how the magnitude of the magnetic field fell off with distance. Lastly, we measured the off-axis magnetic fields. We did this by starting with the same setup and finding the distance perpendicular from the magnet to the magnetometer, where B net equaled 100 microteslas, and then moving my phone up at that distance. Next, we've measured the D and the X and Y and Z components of the magnetic field. We repeated this 2 times, and then we took that average. Experimental observations. So here are the 4 statements we were given. The ones I observed in green are these 2. When the magnetometer is far away from the magnet, it measures the near zero magnetic field in the X direction. And we also observed that as the magnetometer moves closer to the magnet, the measured X component of the magnetic field increases. These 2 were not observed in our experiment. So as the magnetometer moves closer to the magnet, the measured X component of the magnetic field decreases, and the position of the magnetometer has no effect on the measured X component of the magnetic field. These were not true. So here's our data from our experiment. You can pause the video here to look at these. And here's the calculations we used. We were solving for the magnetic dipole moment. So we started with this equation, and we set it equal to this one to find the magnitude of B. And we were solving for mu here. So here's the final result, which we'll use later. And then here is our distance dependence equation, but we put everything to the natural log for our graph. And then here we have our, we can look at our slope, which was in y equals mx plus b. We can look at our graph for that and find these values. So n was from our graph, and we also found our ln of k, which we could raise everything to e and then get this value. And then we took that back to the equation we just found, plugged everything in. We did have to approximate the n, our slope, to make everything work out. But here's our final value, so 0.0915. Here's our code, physical constants right here. Here's our scaling values we used and the distance for that. This was the code for creating a magnet at the origin. This is the function we made to calculate magnetic field. Down here we have the arrows we made for our, this is us making the 45-degree arrow and calculating that. Up here is our setting the distances for our observation locations. This is our on-axis arrows, and this is our perpendicular arrows. So this is what our code looks like after we run it. You can see the on-axis and the ones perpendicular, and there's our 45-degree arrow up there. Plus here's all the outputs. And then here's our magnetic field at the 45, which was what we measured in our lab experiment. So what I did is I'm going to take these and find the magnitude of this. And then once we do that, we're going to compare them. So this is what we got from our computational model versus what we got in our lab. So they're not too similar, but they're pretty close, so not too bad. Now for the discussion. What if you hadn't oriented your experiment to compensate for the magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? Okay, that's definitely going to mess with your graph a lot because we had to zero everything out. If we didn't change for that, then we're going to have some like initial x component, and that's going to mess with the values. What if you were to stick two identical magnets together and to end and run the experiment again? How would you expect your measurements to differ? Not too much. The directions would all be the same, but the magnitudes are going to be different because it's a